This is the current state of the homework 1 part 1. You can see distribution is very wide. Some people didn't even start it. Some already finished it. And more importantly, timing is different. The same amount of problems, same number of problems requires different amount of time from different people. Of course, it depends on many different circumstances. But you never know how much time it would require for you until you try it. And if you haven't tried it and still waiting, you're at risk. So if you, one of these persons, what you should do today, right after lecture, open assignment and read it. That's it. You know that those are different mental actions, reading and solving. They don't have to be coupled together. If you just read it, it takes 10 minutes, no more. Your brain, even if you don't know it, starts thinking about it. At a certain point, you may get a feeling, oh, I know how to solve problem number 4. Solve problem number 4. That's it. But again, the best strategy is not waiting till the deadline and, well, you're going to do your homework, I'm going to do my homework. The notes for the lab are posted on the blackboard, but I just want to make a note about the first part. It's about right triangle. People have been using this approach to measure distances, not reachable distances, for hundreds of years. It's just a straightforward application of what we know about right triangles. Now, so this is the last problem from yesterday. But today, first, I want to ask you a question. So please read the question. I'll be back. You don't have to see me in order to hear me, so keep thinking. All right. This problem is about 2 balls, but it doesn't have to be balls. I like this experiment with a physics textbook, which is very, very heavy, and a piece of paper, which is very, very light. All we need to do is just release them from same height and see what's going to happen. That's, well, going to be proving one of these answers. So all we have to do just pray first, drop second. So what happened? The book reached first. Do you think the same should happen in this situation with the balls? I actually have balls. I just like the book. Balls. What's the difference? In this situation, the heavy object hits the first. In this situation, this is heavier. There is no difference. Why do you think we observe this? Same experiment. You want to see it again? Please tell me. What's the difference between using sheet of paper and a ball? Air resistance. That's a hypothesis. We have to check it. And how can we check it? We have two options. Number one, we can seal up this room and suck out all the air. We will die, but physics will survive, right? But there's a different way. What can we do about this? We can decrease the size so it wouldn't matter anymore. Like a ball. That's it. So if we neglect air resistance, the weight doesn't matter. All objects falling down in exactly the same way. I hope that's what you said. And if you go to these links, you actually can see a video of a similar experiment on the moon. The moon has no air, so no air resistance. So a hammer and a feather fall down and hit the ground at the same time. Well, it tells us something very important. It tells us that all objects falling down with the same acceleration, which we will calculate, and we know already basically from different experiments. This is a standard motion diagram for a ball falling down, released from rest, like this again. And please, anybody, what is missing on the left? Something is missing. Something without what? Neither graphs nor data could have been collected. Yes?
Origin.
Well, origin is a dot. It's a spot. It's a point. It's a single location. I can do that, but that's not enough to get all the numbers. Where else should be? Yes? I'm not sure how that would help to get those data. Those data have been measured using Lecture4 interface. That's actually used to be a demonstration in a lab. You just attach it, drop the ball, measure. Those are data. Yes? Well, kind of put origin already. How did we get the numbers? Say something. I'm not going to give up on you. Anything? No, I don't see any equations, and I don't need any equations. It's an experiment. It's an experiment. Experimental data, yes. It is in vacuum, yeah. Physicist who did that survived, but he used something very specific, which is not shown on this picture, to get those numbers. Yes? Sensor, what does a sensor do? Measures distance, measures positions. What else can we use to measure a position of an object? Yes? We cannot use equation to measure things. We use equations to calculate things. To measure things, we use measuring devices. And lecture number 1, we talked about 3 different standards, 3 types of measuring devices. What do we use to measure mass? What measuring device? Scale. What measuring device we use to measure time? Watch, clock. What measuring device we use to measure distances? Cannot hear you. Ruler, measuring tape, ruler. This guy. How do we use these numbers? We look at them, right? And then we write them down. But this ruler, when it's used in physics, has a very special name, in mathematics as well. What name is that? We used it before. A special name for a ruler or measuring tape. We use it. We use one of these to describe one-dimensional motion, two-dimensional, three-dimensional axis. Yeah, it's not axis of evil. It's just axis. So, and the axis, how does it look like? How does it look like? What is the shape of an axis? Straight line. You know everything. So just say it. So how do we draw it? Vertically, because we could have drawn it horizontally or at 45 degrees. But in this situation, of course, the axis is a vertical straight line with the origin. Here, I know it's here because I see this number. What is still missing on this axis? Direction. So how does it point? Up or down? All right, I see deep conflicted answers. If you think it points up, please raise your hand. If you think it points down, please raise your hand. Thank you. Now, so this was 0. This was negative 0.049. And this number negative 0.196. And this number is negative 0.441. And here we have negative 1.225. So what is happening to the numbers? They're getting more and more negative. So what does it mean? How does it point? What is the positive direction of the axis? Up. Well, the only thing is, normally, for a vertical coordinate, for the vertical position, for the vertical axis, we don't use a letter X anymore. We just use letter Y, which, of course, doesn't really matter, just a convention. So without the axis, everything else would have been absolutely impossible. We need the axis. We have to choose the origin. We have to point the axis in a certain direction. And technically, we could have directed it up or down, but all right. Before I go to but, I want to ask you this question. What do you think about the acceleration of this ball? How does that point? This is the ball. Now it is at rest, and I release it. It starts falling down. For every mechanical motion, we have a special name. Specific case of the motion when object is not moving is called rest. Specific name for a motion when object travels in the same direction, same distance over same time, has a name, motion with constant velocity. Specific motion when object travels and velocity changes by the same amount over same time has a name, motion with constant acceleration. What kind of a motion is this one? Is it rest? No. Is it the motion with constant velocity? No. Is it the motion with constant acceleration? Yes. It's constant, it has fixed magnitude, it has fixed direction. How does it point? Well, the initial velocity was 0. It travels faster. Second later, velocity is not 0 anymore. How does velocity point, by the way? You got to say something. Down, so why wait so long? Velocity points down. Now, speed is the magnitude of velocity. What is happening to the speed? Increases. First of all, the question, what is happening, in general, may have two answers. First, nothing. Second, something. If something is happening, you also have two options, increases or decreases. So it's always just dichotomic thinking, with choice, making choice between two options. You just need to know the options. Changes, yes. How? Increases. How do we call this situation when speed increases? Speeding up. And when object is speeding up, what do we know about the direction of velocity and acceleration? They have to be the same. So acceleration must point down. That's the logic. And of course, yeah. So to demonstrate that fact, we use a little arrow, and we write a variable which demonstrates physical quantity acceleration. Done. So the standard letter for the magnitude of this acceleration is lowercase g. It's about 9.8, and when you do a homework problem, you have to use 9.8, but in a class and on the exam, we're going to be using 10, because 10 is a good number, very simple to use. Okay? Now, please tell me what you think. Do you see the difference between this slide and the previous slides? And what is the difference? Is it the same object or different? What do you think? No, the same? Exactly the same picture, same hand, same ball. So the object is the same. It falls down, same motion. What is the difference? Huh? What is the difference? What do you think? What do you see different? Well, that's the question. The situation which should bring the difference in the answer is in the picture on the left of the slide. So do you see any difference between this slide and the first slide, the previous slide? The origin is at a different location, and where else? Where else is different? Yep, direction of the axis. So there is no law which prevents us from directing axis down. Again, nature doesn't have axis because nature doesn't need axis. We need it. Nature doesn't need origins. We need it. So we choose. It's completely up to us. But if we choose it differently, all those numbers become wrong relative to this choice, And what about acceleration? What will be the direction of acceleration now? Why would it be up? You see? I tricked you. All I've done is flip the ruler. By me flipping the ruler, do I change the nature? Of course not. The nature doesn't care. If I flip the ruler, acceleration cannot be affected at all. If I flip the ruler, acceleration still must point, as it pointed, down. But relative to the new direction of the axis, it becomes positive. Same ball, initial velocity is 0. In a second, velocity is not 0 anymore. And it's speeding up. If it's speeding up, acceleration should point the same direction as velocity points, so still down. But relative to this axis, remember, we talked about it. If velocity or acceleration point in the opposite direction, it's negative. But if it points in the same direction, it's positive. So the magnitude of the acceleration, of course, is the same. But the value which we would have to use in equations will be different. Equations depend on the choice of the direction of the axis. That's why never choose it down, always point it up, and you will be all set for the rest of your life. Always point vertical axis upward. Where do you want to choose the origin? That doesn't really matter. Normally, it's either at the initial location, or the final location, or the lowest location. The lowest usually is the most convenient one, because in that case, all your values will be positive. They will be above 0. Well, so just the summary. And now these are equations for any motion like that. This motion has a name, a free fall, because the object falling freely, neglecting air friction. We neglect air friction. So nothing is acting on this object except force of gravity, because the Earth attracts it. But nothing else. Free to move. Now, we know if I let it go, it's speeding up. But if I toss it up, it slows down, right? So when it slows down, what is the direction of acceleration of this ball? Well, I don't understand. You know, the answer should be up, down, left, right, still down, because it doesn't matter how I toss the ball. Acceleration always points toward the ground. The Earth pulls it. And of course, when it slows down, acceleration should point opposite to velocity. But if it moves up, opposite to up means down. Acceleration always points down. Free fall acceleration. It just, in this situation, some people 50 years ago would call it deceleration, which is wrong. Don't do that. So, because it's a motion with constant acceleration, the equations, so same well-known equations we used before, we just use a different letter for acceleration, which tells us it's a fixed number, which is equal to 9.8 at home and 10 here. Any questions? Because this completes the whole thing about free fall. We know everything. Now we can go back to this problem, and I'm going to give you 1 minute to draw a picture. This is an experiment which has been used hundreds of years ago to actually measure this acceleration. dropping the ball, measuring time. So yesterday we already said, and the initial velocity was 0. It was released just, and it was 49 meters above the ground. Now, what does this picture miss right now? That was the first question we answered today. What should be added? Axis. So you have to draw the axis. Would be horizontal axis helpful? No. The motion is vertical. Horizontal axis doesn't matter at all. So vertical axis. How do we point it? Always upward. Where do you want to choose the origin? Well, here we have two natural choices, either initial or ground. I choose ground because that's the lowest location, and it makes everything positive. In that case, x initial automatically equals 49 meters. X final automatically is 0 meters. And since everything is about x's on this picture, I start from the motion. I use x's, okay. Doesn't matter, you can use y's. I switch to y's next time. X initial plus v initial times time plus 1/2 acceleration time squared. This is a standard motion equation for any motion with constant acceleration. However, in our case, the acceleration is a fixed number. The acceleration points down, and relative to our choice of y, well, x-axis, it's negative. So that's 0. That's 0. This is 49, and this is negative 10. Oi, sorry, we don't know it. That's what we're looking for. Scratch it, scratch it, scratch it, scratch it. Don't forget it. This is what we know. 1 second. Even better, easier to calculate. And that's at 0. This is 49. I need more coffee. Just coffee. So, 0, 49, 0. This represents a letter T time. This is 1/2 acceleration, which we are looking for so far. Time is 1 second. Now we just plug in the numbers. 0 equals 49 plus 0 times 1 plus 1/2 times a times 1 squared. Right? Negative 49 times 2. Okay, that should be 4.9. Or it would have been a different planet. So negative 9.8. So it's not 49, it's 4.9. Done. Sorry for the mess. Fixed. So that's how it's been measured. And we need to add the unit, meters per second squared. So when anything is falling down on the Earth, every second its speed 9.8 meters per second higher than a second before. That's it. Starts from 0, in a second 9.8, in a second 9.8 times 2, in a second 9.8 times 3. So it travels faster and faster and faster until it hits the ground. Do you have a question?
Why is it plus 1/2 AT squared?
Because that's the motion equation for any motion with a constant acceleration. Well, of course, we assume in this situation that acceleration is constant. So if we said it out loud, this is the motion with constant acceleration. At this instant, we stop thinking and start writing equations for motion with constant acceleration, which are two. There is a second one, velocity equation. There are two more equations which derived mathematically from these two. But this action does not require any thinking. MCA. These three letters immediately mean x equals x initial plus v initial t plus 1/2 at squared over 2. V equals v initial plus at. Even if you don't know what I wrote, you really know what I wrote. The motion equation, number one equation, and the velocity equation. That's it. That's how it works. You have to make a statement about the type of the motion. The name of the motion immediately tells you what equations should be used. How? That's a completely different story. It depends on each individual problem. For example, this one. A man standing on a roof shoots the ball straight up, and the ball falls down, eventually hits the ground. Well, don't read it, because basically it says, find everything. Everything we can. We will not find everything. It will take the whole lecture. But we can. Everything on this slide can be found. So, what? Well, first, of course, so this is the height of the barn, 5 meters. And the ball was 2 meters above the roof when it was released from the hand, and it should travel upward initially. So it is traveling, and it's slowing down. We know this, because eventually it stops, reverses its direction, and starts falling down. So the trajectory looks like this. Kinda. Technically it should be straight vertical line, but it's okay. So this is just a picture. But if we add one more element to this picture, it will become a diagram. What element do we need to add? Axis. So add. How do we point it? Up. Where do we choose the origin? On the ground. That makes the initial coordinate of this ball equal to what number? 7. Yeah, 5 meters from the bar plus 2 meters. It was held above it, so 5 plus 2, 7 meters. So technically, there are different approaches to this problem. First of all, if you flip it in your mind by 90 degrees, it will be very similar to problem number 3 on the homework. Yeah. Left, right, now up, down. So we can treat this part of the motion individually, this part of the motion individually, or we can analyze the whole motion at the same time. And for each part of the reasoning, we can write exactly same equations. Because when it flies up, its acceleration is constant, which is equal to 9.8 meters per second squared. When it's falling down, acceleration is constant. So since it is a motion with constant acceleration, the equations, and let's finally call it y. The equation for the motion with constant acceleration, it's Friday. Today's 13, no? No. The velocity equation, the motion equation, is exactly the same as for any motion with constant acceleration. But in this situation, we also know that acceleration equals, well, roughly negative 10 meters per second squared. That's it. That's an additional information. And we can apply these equations to the motion, well, from initial to the top, from the top to the ground, or from initial to the ground. It's up to us. Well, this is a special point. We know something very important about it. It momentarily stops. So V top equals 0. This is important information. And when I'm not solving a problem yet. I'm not looking for unknowns. I'm analyzing the situation. That's it. And when I'm analyzing the situation, I just ask myself the same question. What do I know? What else do I know? What else do I know? And I put that information in front of me so I could use it later when I need to solve it. So what do I know about the highest point? The velocity at the highest point is 0. That information has to be a part of the reasoning, so I write it down. Now, all right. 1, 2, 3. Let's pick up first case. What can we write down? Well, for the velocity equation, 0 will be equal to the initial velocity was 10. I didn't put it. 10 minus 10 times time. So again, my acceleration is not 9.8, it's 10. And y at the top will be equal to y initial plus the initial velocity times time plus negative 10 times time squared over 2. This is a special time. This is time to get from the initial location to the highest. And that's what people in physics call time to the top, or time up, or time one. But you should use some kind of a subscript to indicate that's not a general time, that's a specific time to get from initial to the highest. And of course, you can see immediately you can solve it, and you can calculate time. Time to the top will be equal to 1 second, and that immediately gives you this is y top, which should be 7 plus 10 minus 10 over 2, right? So 12, right? So, no, yes. 17 minus 5, 12 meters. So this is measured from the ground, 12 meters above the ground. It stops there. Now I want to see what's going to happen if I use, well, the whole trip. Yeah. For the whole trip, velocity equation. Velocity when it hits the ground, v, let's call it final. We don't know it. So initial is 10 minus 10 times total time. We don't know it. Well, so that's all we can write. Now the motion equation. When it hits the ground, hits the ground, its coordinate has a special value. What is value? When it hits the ground, y equals what? 0, 0. The initial y is 7. Speed is still 10 initial. 1/2 negative 10 times squared over 2. And we have to remember, that's a special time, the time for the whole trip total. Well, if you look at this equation, it has only one unknown in it, time. So you can solve it, although that's not a simple linear equation. It's a quadratic equation. You have to use a quadratic formula. You have to refresh how to calculate discriminant, yeah, et cetera, et cetera. But it's doable. So that's another approach. And of course, you can apply the same equations to the part number 2, and I'm not going to do that. It's not interesting. There's a question on a homework. Let's say your friend or enemy, I don't know, catches the ball 1 meter above the ground. So how fast would the ball travel at that instant? V1. Well, what can we, well, technically that's a kind of part 4. Yeah. What can we try? We can try it using both equations, right? For example, V1 should be equal to, I'm using the velocity equation. So it has 4 letters, V, V initial, A, and T. And when I use it, I have to replace each letter with a number if I know a number. Or I just have to keep a letter if I don't know a number. So I don't know a number. I know this number. I know this number. And I don't know this time. I don't know how much time would it take to reach that point. So, but that's all I can write. Well, let's see what we can do about this situation using motion equation. So for this situation, the final coordinate is 1. The initial is 7. Initial velocity time 1, negative 10 times 1 squared over 2. All right. This is a quadratic equation. We can solve it using quadratic formula. Calculate time, and when we calculate time, we can plug it into this equation, calculate speed. But we know that technically, we could use other equations. The equation which has been derived from two fundamental equations, mathematically, relates initial velocity, final velocity, acceleration, and displacement. So, if we use this equation, that would have been the velocity we're looking for squared. This is 10 squared plus 2 times acceleration is negative 10, always negative 10. Now, delta y, that's a displacement of this ball from initial, which was 7 meters above, to the final, which is 1 meter above. And displacement always final minus initial. That's what the displacement is, final minus initial. So final minus initial, that's equation which easier to solve. Yes? Because that's the problem I am solving right now. I'm not solving case 1, case 2, case 3. I've invented a new problem. I called it case 4. And in this problem, the ball was caught. 1 meter above the ground. And I've solved that problem. That's it. And you can see that, for example, solving the problem number 4, calculating that velocity, we had different approaches. Which is easier? There is no such thing as easier. It has to be tried. It has to be tested at home. And you should choose whichever you like, whichever you don't like, which feels better for you personally. It's just a matter of trial and error, matter of practice. That's it, nothing else. And here, you can check the answers for different situations. That's quadratic equation solved. And one more example, very quickly. A standard problem when two different motions are combined together. Here, first you drive in a car at 20 meters per second, which means motion with constant velocity. But then you see a deer, the same deer, and you apply the brakes, and eventually you stop. But depending on situations, you may stop way before the deer, just barely touch it or hit it hard. So the question is, what should be that acceleration, critical acceleration, so you wouldn't hit the deer in this situation? Of course, we need to draw a picture. So a car was traveling at 20 meters per second. And from this instant, right here, 60 meters away from you, you see a deer. It takes you 1 second time reaction to react and apply the brake. So for 1 second, you will be just traveling at 20 meters per second. And then you are applying the brakes, and you're slowing down. And the situation we are looking for is when you just scared the deer, just barely touched the deer. So distance traveled from this location to the deer will be equal to 60 meters minus, how much did you travel? d1. Here, your velocity still was equal to 20 meters per second, and here you stopped, which means your final velocity becomes 0. That's what we know. That's it. So, you see, when you draw and speak simultaneously, it helps you to solve the problem. It helps you to make connections between the things in the problem. And, well, first thing to do is calculate this distance, of course. It's displacement when velocity was constant. For the motion with constant velocity, this is how we relate distance, speed, and time. And the speed was 20, and time reaction was 1 second. So you traveled 20 meters before you applied the brakes, which means the distance traveled after that was 60 minus 20, 40 meters. Let's call it L. This is the distance when you've been traveling with constant acceleration. So motion with constant acceleration, v equals v initial plus acceleration times time. Well, just for the sake, x equals x initial plus v initial time plus 1/2 acceleration time squared. So this action doesn't require thinking, doesn't require understanding. It requires enacting. MCA means write down these equations. Next step also doesn't require thinking. Now we just start throwing in all the numbers we know. What do we know? Well, we know the final velocity is 0. You stop. The initial was 20 plus acceleration times time. That's it. So go to the next equation. Well, for the next equation, we should choose the origin. And the motion with constant acceleration begins here. So I choose the origin there. So my initial location will be 0. The initial velocity is 20. 1/2 acceleration time squared. And my final will be 40 meters away. This is a quadratic equation, so we definitely can solve it, but it's not going to help because acceleration is not known. So we have two options here. Number one, we can solve the first equation for time, plug it in this equation, rearrange it, and solve it for acceleration. In the end of this process, we will get the acceleration, the equation which relates acceleration, initial speed, final speed, and displacement. The third equation which has no name. Final squared equals initial squared plus 2 times a plus displacement. Final speed is 0. Initial speed is 20. Acceleration equals, we don't know acceleration, but displacement equals 40. And this equation is solvable. So I want to stress that it's your choice. Every time when something like that happens, when you have two equations with two unknowns, do it algebraically, or apply an equation which has been derived, but I still would recommend to derive it once to see how it works in general. Well, acceleration will be, actually, please tell me. Anybody? This acceleration, will it be positive or negative? Negative. Because velocity points to the right, velocity is positive, but it slows down, so acceleration should be opposite to velocity. It makes it pointing to the left. That makes it negative. And of course, calculation supports this. Acceleration will be equal to negative 20 squared over 2 times 40. No, actually, I don't want to do that. I want to keep this because now I can cancel this. I can cancel this. So it's going to be negative 5, right? Any questions? The whole point of these two classes is every time when you know that the motion described in a problem happening with a constant acceleration, you stop thinking. You start writing equations. Equations for the motion with the constant acceleration. As many times as you can. For each individual part of the motion, you can write 2 equations. And then just throw information into the equations and see where will it lead you. Eventually, it will lead you to the answers. All right, so we saw this slide. It's about a definition of a displacement. A displacement is an arrow, and if it's an arrow which points from one point to another point, all we need is 2 points. We don't need anything else. But any motion can be described as a combination of displacements. So to describe a motion, we use arrows many, many times, heavily. And in physics, if something is being used again and again and again, that makes it important. And if it's important, we give it a special name, and we study its properties. So we don't call it an arrow anymore. We call it a vector. And the property of any vector is it has to be straight. It has certain magnitude. It has a direction. It points somewhere. And based on this definition, please tell me how many vectors do you see on this slide? Use Weber sign. How many vectors do you see? You're asking or you're saying? So if there is a certain information which you think would help you to answer this question, what should you do? You should ask for that missing information. So you should be acting. You should have said, Mr. V, can a vector has 2 directions? All right. In that case, we go back to the definition. This is a definition. Vector looks like this. Has to be straight, point in a certain direction. Does it help to answer my question? How many vectors do you see? Now, how many vectors do you see? Now, how many vectors do you see? You saying or you asking? Yeah. All right. So, is this a vector? What's wrong with that? Okay, cross it out. Is this a vector? What's wrong with that? All right, cross it out. Is this a vector? Why? Well, this is the definition. According to the definition, how many directions does it have? 1. This has, so is this a vector? No. It violates at least a portion of a definition. If it violates at least a portion of a definition, it violates the whole definition, it's not a vector. Okay, so not a vector, not a vector, not a vector. Is this a vector? Yeah, it completely fits into the definition. Is this a vector? That's it. 2 vectors. So we have special vectors. We already know displacement, and we know velocity and acceleration. We'll talk, but there is one additional very important vector. We call it a position vector. To describe a position of an object relative to something, first we have to choose the origin, and then we can draw a vector from the origin toward an object. So for example, if this is the initial position, this will be the initial position vector. However, we also call it in physics radius vector. That's why very often we use the letter R for position vectors, initial. Then, if the object has moved, we can draw a vector we used to call a displacement. Okay. And the new position, the final position, also can be described by a vector which goes from the origin toward the final position vector. Now, what did we do? We got initial position vector, and we added displacement, and we got a result, or people call it resultant. And this is one of the many reasons vectors are important in physics. So in mathematics, what symbol do we use to replace the word add? Plus. So this is basically the idea for how will we be adding vectors using this type of a triangle. Well, and people don't usually write a letter S when you use position vectors. They use a letter R for everything. So this symbol represents a displacement from here to here. It doesn't matter how it's been displaced. Yeah. Initial, final, the displacement. And if we use mathematics natively, naturally for us, the displacement will be equal to difference between final and initial. This symbol, little triangle, in physics always has exactly the same meaning. This whole slide has importance only here at the bottom. This symbol, it's a capital delta, Greek letter, always means the same, final minus initial. What final in initial? Well, it depends if it's radius. So final radius minus initial radius. It's temperature, final temperature minus initial temperature. It's, if it's time, final time minus initial time. Every time when you see this symbol, it means final value minus initial value of that quantity. Now, how do we describe vectors mathematically? Well, first, because it has a length, we can take a ruler and measure. That will be the first number we always can assign to a vector, its length. In this situation, well, first we need to assign a letter. Let's call it vector A. And magnitude or length of this vector equals, I can see, 42 millimeters. That's it. We just look at it. Second number, which describes a vector, is an angle. We have to use it to describe how does it point. And according to a standard agreement, unless something else said, we measure angles from positive x direction counterclockwise until we reach the vector. So in this situation, this angle, well, theta, will be about, so 180 plus 210 degrees. We could have measured it in opposite direction. People do that. But if we measure it clockwise, let's call it alpha, we should assign a negative number. So that's going to be 360 minus 210. What is it? Well, 210 technically minus 360. 150, right? There's one more thing I want to mention right now, but we'll talk about it a little bit later, because your calculators might do that. To measure angles, we don't use degrees only. We also use what? Radians. So you need to know the conversion factor, and well, pi radians is an equivalent of 180 degrees. So you can switch back and forth. Well, we know what we can do to numbers: multiply, subtract, etc., etc. We also need to know what can we do to vectors. First, what happens if we multiply a vector by a number? The number changes its magnitude and may change its direction. So if we multiply by a positive number, we preserve the direction. We keep the same direction, but we change the magnitude accordingly. So this is a vector A, and this is a vector 2A. This is a vector A. And here we should have magnitude twice of the original, but because of the negative, we have to change the direction to the opposite. Now, well, it doesn't have to be a whole number, it could be a fraction, doesn't matter. Coefficient changes the length, the magnitude. Now, addition. We already know the idea. The idea comes from here. But now we have to convert this idea into an actual rule. And the actual rule has a name, a tail to a head. It has two steps. If you need to add two vectors, you have to follow a special procedure. First, you have to rearrange vectors in such a way so the, well, you can call it head or arrowhead of one vector and tail or beginning of a second vector coincide, like in this situation. That's the first step. Second step, you have to connect 2 points, the very first point with the very last point. So let's do it. Let's do it just as an example. Any two arbitrary vectors. I don't know. Let's call it A, and let's call it B. Our goal is to draw a vector which should be equal to the sum according to the tail to a head rule. Well, first step, we need to shift at least one vector. Well, I cannot damage the screen, so I have to do it here. So this is what I can do. I just can cut the vector. Oops. And now I can shift it toward the first. And now the tail and the head put together. However, when you do that, you must preserve, keep the direction. Because doing it like this is wrong. Do it like this is wrong. You're changing the vector. It will be different with different direction. So this is what we do. But of course, You don't have to cut your paper every time when you need to add two vectors. This is when you have to use your what? Imagination. You imagining that you cut it out. So how do we preserve the length? We use a ruler. This is the same vector B shifted in such a way, so now the tail and the head of these vectors put together. That's the first step of the procedure. Second step, we have to connect 2 points. So the beginning and the end. We can imagine that someone is actually walking. And in that case, what we're drawing is kind of displacement, the result of that walk. And are we done? That's a yes or no question. Now, what's missing? The direction. It also must be a vector, so it also must have an arrowhead. How do we point it? Well, if that our imaginary start, and we walk and we walk and we walk and we walk, that's our imaginary finish. It has to point from start to finish. That's how we point it. So this violet arrow represents the resultant, which is the result of this procedure, which we call the vector addition. And every time when we need to add vectors, we have to follow this procedure. Step 1, step 2, step 1, step 2, move, connect, move, connect. That's it. So in this situation, next step would have been, again, using protractors and rulers. And actually, that's a good thing to do. So the magnitude of A equals 10 centimeters. Oh, I have a very good eye. The magnitude of B is equal to 6 centimeters. And the magnitude of C is equal to 12 centimeters. How do I know? I know how to use the ruler. Now, this expression mathematically represents the procedure, vector addition. But if we look at the numbers, A plus B equals 10 plus 6, 16. But the magnitude of C is 12. What does it prove? It proves we cannot treat vectors as numbers. We cannot just add the magnitudes because the result will be wrong. By adding vectors, the magnitude of the resultant is 12. And 12 is not 16. And this is a very common mistake when people use vector addition. They forget that vectors are not numbers. Treat them as numbers and get wrong results. Don't answer this question. Just remember this fact because I just have it proved. If we have a sum of two vectors, this statement will be wrong. On a previous slide, I had this statement in words. This is just, I have it as an equation. So how do we read it? The magnitude of the sum is not equal to the sum of the magnitudes. That's how we read it. The magnitude of the sum is not equal to the sum of the magnitudes. Well, if we have more vectors which we need to add together, we just have to repeat the procedure again and again and again. And with vectors, like with numbers, the order don't matter. We can add them in any order. We can reorder a plus b plus c, b plus c plus a, c plus a plus b. The result will be the same. Now, components. This is a tricky variable because the same word, component, has different meanings. This is one of those meanings. So, a component of a vector is another vector. That's the first part. Now, every vector has several components. Well, in general, maybe 3. In our situation, 2. And those component vectors must obey these rules. First, they must be parallel to x and y axes. And second, when we add them together, we get the original vector. Well, an example. Not very good. Let's do it this way. These blue arrows, I hope, represent components of vector A. You should tell me if I'm right or wrong. You say wrong, I see you move. What part of the definition do they violate? They're not parallel. They give together the original vector according to a tail to a head rule, but they're not parallel to the axis. So those are not components. Wrong. Well, what about this? Parallel to y, parallel to x. Why? You say no. What's wrong? Exactly. So if I add these two blue arrows, the result should point toward the origin. But original vector points away from it. Wrong. So what should I do? Well, the technique is simple. First, we just draw kind of two lines perpendicular to each other. And then we draw an arrow which parallel to one axis. That will be y component of this vector. And then we draw an arrow which is parallel to x axis. And that will be the x component of this vector A. And this procedure has a name, a resolution. We have resolved vector into components. Now, what's good about components? Right triangle. What do we know about right triangles? There's one word which answers that question. Everything. That's it. So by transition property now, we know everything about components and how they're related to original vector. We know components, we can get the vector. We know vector, we can get components. It's all about geometry and nothing else. And the problem is to keep track of what does your letter which you use specifically represent. For example, here in this triangle, this symbol represents the magnitude of y component of vector A. And it has to be equal to hypotenuse times sine. But writing down all equations, keeping all these little arrows of vertical bars is just exhausting. It's impossible. It takes too much time. That's why we don't do that. That's why we write the same equations, but we keep in mind the actual meaning of each variable. That's supposed to be the length of the original vector. That's supposed to be the length of the y component, etc., etc. And another set of equations which we can use, Pythagorean theorem, tangent. But here you don't see those little arrows anymore, vertical bars. You have to know that those variables represent magnitudes of those lengths of those sides. A second meaning of the same word component is kind of identical to what some people call coordinate of a vector, not coordinate of an object, coordinate of a vector. And this is an official definition of that. First of all, it's not a vector anymore, it is a number. But that number can be positive or negative. The x component or x coordinate of a vector is a number which is equal to the magnitude of the x vector component when it points in a positive y direction, or say magnitude times -1 when it points in opposite direction. So the definition looks kind of long and complicated, but in reality, the technique is very simple. So this vector and the components of this vector together should form right for a triangle with sides 3, 4, and 5. So I can draw two lines first, parallel to each axis. That will be 90 degrees angle. This side should represent the y component. Well, let's call it A. So that's going to be y component of vector A. Well, I have to point it because together y component and the x component, if we add them up, should provide the original vector. That will be the x component. Now, the magnitude of this equals, please tell me, 3, 4, and 5. 3, it's the shortest one. The magnitude of this equals 5. The magnitude of this equals 4. Now, I want to write the actual value for each component of this vector. So what do? Well, first, I know it should be a plus or a minus. The magnitude of the vector component, a plus or a minus. And now I have to choose a plus or a minus. That depends on the direction. Y component. It points in the same direction with the y-axis. So y component should be positive. X component. X component points opposite to the x-axis, so x component should be negative. Done. And we also call them x coordinates of vector A. And of course, using numbers is much easier than arrows. So for every calculation, normally we use this type of components, coordinates. Before. So why do we need to know components? Because when we know components, we can add vectors purely algebraically. This is an example. Vector A, vector B, the resultant. In this example, we can see that if we know the x component of A and know x component of B and add them up together, we get the x component of the resultant of the sum. If we know the y component of A and the y component of B and add them up together, that gives the y component of the resultant. And now for this resultant, because it is also a vector, it forms a right triangle with its components, the magnitude of the resultant and the components of the resultant related by standard geometrical equations. So this is a standard approach we could use when we need to add two vectors algebraically. we need to know the x component of the first vector, the y component of the first vector, the x component of the second vector, the y component of the second vector. We add them up as numbers. And then we get the magnitude of the resultant, direction of the resultant, because we know everything about right triangles. All right, so that's the theory. Now example. Here we have a vector with a given magnitude at a given direction, and we need to calculate the components. Well, we cannot calculate components until we see those components. So first we have to draw those components as vectors. Again, the procedure is simple. First, draw line which is parallel to one of the axes. Second automatically is here. Yeah. So now, this segment should represent the x component of this vector. This segment should represent the y component, but I have to add arrowheads. And to do that, I need to know that cx plus cy should be equal to c if we add them as vectors using a tail to a head rule, which means automatically cx should point to the right, cy should point down. Now we have a right triangle. This is 32. This is 68 degrees. 68 degrees. So if I want to calculate the magnitude of the x component, well, I have to use cosine 32 times cosine of 68. If I want to calculate the magnitude of the y component, I have to use sine. It's opposite to this. So 32 times sine of 68. But these equations don't give us actual values. They give us only magnitudes. So we have to make an extra step. The actual component might be positive or negative depending on the direction. For example, cx, positive or negative? Positive because it points in the direction of axis. So wherever it is. cy, negative because it points opposite to the y-axis. So the actual value of this component will be this. That's how it works. And that's why geometry kind of is important. Any questions? One more. Have a nice weekend, long. Do your homework. I'm going to do mine. Thank you. Yes, I'm listening.
For the last 2 days, I got here exactly at 8:30. I didn't know there was a sign-in sheet, so I didn't sign in for Wednesday and Thursday.
You should send me an email with.
Okay, thank you.
Yeah. The door is open, right? Don't rush. Everything should be done slowly because I have to check this. All right. Thank you. You can just anywhere in the room you can park. Yes.
Hi, I'm Jessica. So I wasn't here the first day, so I have this for you.
Thanks.
Yes, thank you.
Hi, Professor. I came last 2 days, but I didn't sign the sign-in sheet.
You have to send me an email. Yep. Send me an email with this information. Yes.
Hi,
I'm Kelly. I'm pretty sure he just answered my question, but I also didn't realize there was a sign-in for the first until
You
yesterday.
have to send me an email.
Okay, so I'll send you an email with that.
Hi, I'm ET, and I send you an email that I only saved my answer for yesterday's class, but not submitted at the time.